In previous video, we discussed about the temperature distribution in plane Corti flow. And another simple case is temperature distribution in plane poiseuille flow. And we also know very well that the Navier-Stokes equation are second order nonlinear partial differentiation, and there is no any known general method to solve this equation. Only in few special cases exact solution can be obtained with certain assumption about the state of the fluid and configuration of the flow pattern. In this video, we propose to study some useful real problem for which exact solutions are possible. The study incompressible flow with constant fluid property. Study incompressible flow with constant fluid property means if at various points of the flow field all quantities such as velocity, density, pressure associated with the flow field remain unchanged with the time, then the motion is said to be steady. If the velocity depends on time, then motion is said to be unsteady. In steady motion, the various quantities of flow field are the function of the space coordinate and independent of time. In the incompressible fluid motion, the density of the fluid remains unchanged or constant throughout the flow field. So now case is flow between parallel plates. In previous video, a simple solution of the fundamental governing equation can be obtained for the flow between two parallel plates which are kept at a finite distance apart. And we also know that the flow between two parallel plates, the equation of energy for the steady flow between two parallel plates are given by the relation rho Cv into U into delta T by delta x is equal to kappa into del square capital T upon del x square plus del square T upon del y square plus mu into del u by del square, which is the equation number 1, where kappa and mu are taken to be constant. Kappa is thermal conductivity and mu is the viscosity. If the plate are kept at constant temperature, then delta T by delta x is equal to 0. If delta T by delta x is equal to 0, then this equation number 1 become kappa into del square T by del y square is equal to minus mu into del u by del y ka whole square. This is the equation number 2. From equation 2, we calculate the temperature distribution for different situation between the parallel plates. In plane poiseuille flow, we know very well that the plane poiseuille flow is the flow in which flow is due to constant pressure gradient. Both plates are rest and motion is due to constant pressure gradient, and the velocity distribution for the plane poiseuille flow is given by the u upon u maximum is equal to 1 minus y square by v square. And we also discussed in previous video that u upon u maximum is u maximum on the middle of the channel. Now the velocity distribution is given by in plane poiseuille flow is u upon u at maximum is equal to 1 minus y square by b square. So du by dy is equal to minus twice um into y upon b square. Um mean maximum velocity of u. So the equation 3 in this case become k kappa into del square T by del y square is equal to minus mu into du by dy ka whole square. This is equal to minus mu into 4 into um square y square upon b4, which is equal to minus 4 mu um square y square upon b4. So this is the diagram when the both plate are rest at y is equal to lower plate at y is equal to minus b, upper plate is y is equal to plus b, and this in x direction in the flow, and flow is due to constant pressure gradient. So both the plate, if the both plate are kept at the same constant temperature T0, it means the lower plate's temperature is T0 and upper plate temperature is also T0. So in this case boundary conditions are become when y is equal to plus minus b, t is equal to t0. This is the equation number 4. So the solution of the equation is 4 is given by t is equal to minus mu into square upon 3k b4 y4 plus ay plus b. This is the equation number 5. And it is also clear that here a and b, capital A and capital B, are arbitrary constant of integration. So using the boundary condition 4 in equation 5, then we get a is equal to 0 and b is equal to t0 plus square mu into square upon 3 kappa. So our equation 5 become t minus t0 is equal to mu into square upon 3 kappa 1 minus y4 upon b4. This is the equation number 6. In velocity distribution, it is clear that the maximum velocities occur in the middle of the channel. So same case, in the temperature, the maximum temperature occur when dt by dy is equal to 0. And dt by dy is equal to 0, then in this equation become, this gives y is equal to 0. Now, so therefore the maximum temperature exists in the middle of the channel, and it given by Tm minus T0 is equal to mu into square upon 3k. Here T0 is the temperature on both plate. Tm is the maximum temperature at the middle of the channel. Mu is the viscosity. Is the maximum velocity at the middle point. Kappa is the thermal conductivity. This is the equation number 7. And this equation gives the temperature distribution. In diagram figure 2, we have shown in x direction T minus T0 upon Tm minus T0 ratio, and in y direction the ratio of y upon b. In diagram, it is clear that when the value of x is equal to 0 to 1, then in temperature is the maximum and then downward. This is the distance between the point lower plate and upper plate. So this is the temperature distribution in plain poiseuille flow plate, air kept at a equal temperature. Here Tm is the temperature in the middle of the channel. So plain poiseuille flow, in case temperature is given by Tm minus T0 is equal to mu into square upon 3 kappa, where kappa is the thermal conductivity. The plain poiseuille case geometry are useful in many engineering branches. We use this result in these branches and get the appropriate result. Thank you.